Hi there, we're in the middle of chapter 11. It's all about quadratics, and we're going to continue on our journey on what quadratics are all about. So far what we've seen is, let's just say I have a quadratic that looks like this, and I'm supposed to solve. Well, we know that this thing is going to be crossing in a couple different spots. I mean, I don't know where they are. But it's going to look something like this. And so in order to find them, we factor, right? This will be x plus. We want factors of 6. We've got 6 and 1 and 2 and 3. We have to add to 5, so we put these in here, and we can see that our solutions are -2 and -3. That's what we've done so far. What if I would change this? What if I change that number to, let's just say, a 4? Okay, this is still going to cross in a couple spots, but where are they? I can't factor, right? Why not? Well, because which pair adds to 4? Nothing. So I say not factorable. So I have to have a different method in order to find the ones that you can't factor, okay? So far when we do this, a times b is equal to 0, they have to be factorable trinomials. They have to, be a difference of squares, or they have to be one of those trinomials, either the AC method or not AC method, that work perfectly, and then they split into the two binomials. But most things don't, so we have to have another way of solving them. And so we use something called the quadratic formula, all right? The quadratic formula, I'm sure some of you have sung the song to this. If you haven't, I'm certainly not going to do it because I have a lousy voice, but you can always Google it. Let me just write down the formula first of all. We've got this. Now, what is this? Well, first of all, this only works if you have your quadratic in standard form. Not vertex form, not all messed up, but it's got to be in standard form. Then you've got your coefficients, an a and a b and a c. Okay, so here we have it in standard form. We have an a, a b, and a c. We've got 5, 7, and 2. Okay, so all we're going to do is we're going to plug it into this formula, and we're going to find our solutions this way. Now, when we factored, they had to be perfectly factorable trinomials or binomials or whatever we had. This quadratic formula will give you solutions to anything, all right? Whether they're whole numbers, whether they're rational expressions, whether they're imaginary numbers. It'll do anything and everything. So this is a really nice formula to use. It doesn't have to be set up in a certain way at all. So we just plug into the formula and we solve. So you notice there's a radical here, so we're going to have to make sure that we have all of our radical rules in place when we simplify our answer, because we're supposed to, simplify our radicals as needed. Okay, so let's start. Let's start with the one that we see there. We've got 5x squared plus 7x plus 2. All right, so let's write down our equation. 5x squared plus 7x plus 2 equals 0. Now we can compare with our our generic one. Yeah, it's in the right order. A is 5, B is 7, C is 2. So we'll write that down. A is 5, B is 7, and C is 2. Okay, we carry the signs with these. If this was a -7x, this would be a -7. So now we're going to plug all these into this formula here. So we have minus b. Minus b means take the opposite sign of whatever b is. We have a +7 for our b, so we would be using a -7 here. Plus or minus. Why do we have a plus or minus? Well, for one thing, we've got a square root, right? And we know that there's always those two solutions. Plus, we know that on these quadratics, they're going to be crossing in two different spots, so we want both values. Okay? All right, so plus or minus the square root, we've got b squared, so we have 7 squared, minus 4 times a is 5, times c, and c is 2. And this is all over 2 times a. Okay, so that's how we plug in our numbers into the formula. And now it's a matter of simplifying. That's always the hard part. So I'm going to leave that alone for right now. Let's go underneath this radical sign. 7 squared is 49. And 4 times 5 is 20, times 2 is 40. Got a subtraction between those, and 2 times 5 is 10. Okay? So I'm just going to keep whittling away at this thing and trying to get it down as far as I can. All right, what do we have here? We have 49 minus 40, which is 9. All right, now we have the square root of 9, which is 3. Now here, we could say, you know, there's no more simplifying that we can do as it is. So now what we do is we split it off into two different equations. Okay, we're going to take the positive and negative values of 3. So one of them is we have a negative 7 plus 3 over 10. And the other one is the negative value of 3, minus 7 minus 3 over 10. Okay? So here we have a negative 7 plus 3 is negative 4. And this would be negative 2/5. And here we have negative 10, which is negative 1. So there's my two solutions, a negative 2/5 and a negative 1. That's where it's crossing. That's my zeros, that's my x-intercepts, that's my solutions to the equation. So shall we check it? I think we should. Let's check the negative 1 just because it's easier. So I'm going to put in a negative 1 wherever I see an x. Make sure that that's going to equal 0. Negative 1 squared is 1 minus 7 plus 2 equals 0. 7 times negative 1 is a negative 7. So I have 5 minus 7 plus 2 is equal to 0. 5 minus 7 is negative 2, and negative 2 plus 2 is 0. So this does work. And if you took the time to put the fraction one in there, it would also work. Now we can also use the calculator to check to make sure that things are the way they are, the way they're supposed to be. Okay, we can put in our equation here. We can graph it. Oh, I've got that skewed from a previous problem here. We'll get that righted. There we go. All right, boy, this thing is crossing at negative 1, and that's right there, and negative 2/5. Let's check with our table here. Let's see if negative 1 is on there. Yep, that's a 0 right there. We're not going to be able to check the negative 2/5 this way. Why? Because I'm going by whole numbers. So let's do this. Let's see what 2/5 is as a decimal. 2/5 as a decimal is 0.4. Okay, so I'm going to write that down. This is the same thing as negative 0.4. So now what I'm going to want to do is I'm going to go into my table set, which we haven't really done yet, and I want to change my delta table. Right now I've got my change in the table going by ones. I want to change that to tenths so I can see the 0.4. So I want 0.1. That's going to go by tenths now. And here I want my table to start at negative 0.4. Obviously I want to look at this exact point. Okay? So now I'm going to go back to the table, and there it is. Negative 0.4 is 0. So now do you see how my x values are going by tenths rather than ones? Okay? Now it depends on how far out your decimals are here. I mean, if your decimals are, you know, never ending, or they're, you know, 0.33333, you can't find them at all in this table. Then you'd have to trace it. You'd have to do a calculation with a 0 and do it that way, which is what we've already seen. So it just depends on the problem. All right? So here we have and we're not going to want the decimal version of that. We want the negative 2/5. Negative 2/5. No, that's not 2/5. 2/5, comma, negative 1, right? Well done. So in a nutshell, this is what you want for every single quadratic. I mean, obviously if we had something like this, it's much, much quicker to factor and find your solutions, right? But sometimes we can't factor, so then we have to use a quadratic formula. All right, so we have another one. I'm not going to do all of these. Let me get my table set. I'll leave that alone for right now. I'm not going to do all of these because, you know, they're all alike, but I will do a few of these for sure, especially when we have radicals. All right, so we have x squared minus 9x minus 22 equals 0. Okay? It's in standard form, so a is 1, b is negative 9, c is negative 22. Remember, we carry our signs with those. All right? Plugging into the formula, we have x is equal to minus b. Minus b would be the opposite sign of b, so that's a positive 9, plus or minus the square root of b squared minus 4 times a times c. Everything is divided by twice a. Okay, so if you don't remember the formula, always have it written down somewhere where you can see it, and then you can plug stuff in. All right, now it's the simplification process. 9 plus or minus. All right, what is negative 9 squared? Well, that's going to be an 81. And here we have a minus, and then we have 4 times 1 times negative 22. So let's do this. Let's do 4 times negative 22. We don't need the 1 in there because that one's, that's a negative 88. And 2 times 1 is 2. So now we have 81 minus a negative 88, which is like a plus, right? So we have 81 plus 88 for 169. All over 2. And the square root of 169, I believe, is 13. Yep, so this is a nice, simple one again. 13 over 2. Okay, and here's where we split. We have 9 plus 13 over 2, and we have 9 minus 13 over 2. We've got to use this plus minus thing. All right. 9 plus 13 is 22 over 2, which is 11. There's one answer. And 9 minus 13 is a negative 4 over 2, which is negative 2. Right? So these turned out to be nice whole numbers, which makes it, obviously this was factorable. Okay? Two numbers that multiply to 22 and subtract to 9 would be 11 and negative 2. So we could have done this one by factoring. It would have been a lot faster, but we're trying to learn the quadratic formula right now. Okay, so let's get those in there. 11 and negative 2, fantastic. We're supposed to support, what did it say? Something about supporting our answer graphically or whatever. That would just be, you know, putting the equation in here and checking it as far as is it crossing at those particular spots that we just said it was crossing. So there's all different kinds of ways that we can check this. Okay, so here's your negative 2. 11's off the screen, so we can set our window for the max to be at 12 so we can see it. Just scooch it over a bit. There it is. There's 11 and there's negative 2. All right. So now we want to find some that have messy answers, don't we? Messy, messy, messy. I need a new screen, I think. Yeah, I do. Okay, I'm going to pause it and I'll be right back. Okay, so let's try this one. now that I have my new screen. All right, we have minus 5x squared plus 3x minus 1 is equal to 0. So we have a is equal to minus 5, b is equal to 3, and c is equal to negative 1. Right? Negative 5, 3, negative 1. So now we have x is equal to the opposite sign of b. We have a positive 3, so we want to make it negative. And we have 3 squared minus 4 times a times c. And that is all over twice a. Simplify. Why is that always the hardest part? I don't know. 3 squared is 9. It's like when we do calculus, we do this one little piece of calculus and then we do 10 minutes of algebra. That's why algebra is so important. All right, so I'm subtracting, and I've got a 4 times 5 is negative 20. Negative 20 times negative 1 is a positive 20. And 2 times negative 5 is negative 10. All right, 9 minus 20 is what? Negative 11? Uh-oh. Now what? How can I take the square root of a negative? I can't. Right? Second function square root of negative 11 is non-real. All right. Now we're going to see later in this section how to do these when they're imaginary. Okay, because these have imaginary answers. This particular equation, well, let's take a look at it. Clear out. I gotta get that out of there. Okay, so let's take a look at it. We've got negative 5x squared. Since I have an imaginary solutions, non-real, this thing should be hanging in the air and not crossing the x-axis at all. Otherwise, there's something wrong. Yep. Look at that. It doesn't touch the x-axis. We'll do zoom 6 because we were a little skewed there. See how it doesn't even touch? That's an indication that we have complex solutions. Okay. Plus, we have a negative underneath this radical sign, so that means there's no real solutions. Now, for right now, we're just going to go into there are no real solutions. Okay. Later, when it says look for the complex solutions, then we have to actually start reducing this down. We know how to do that. But for right now, in this particular point in the lesson, we're just going to say there aren't any real solutions. Now, further along, right here, see how we want we want the complex solutions, write complex solutions in standard form. All right, so we will hit them. So if it asks you to not hit them yet, which is over here, which is just saying there aren't any real ones, that's what you put. All right, what about something like this? What's the issue? Well, I think the issue here is that it's not in standard form. It doesn't look like this, does it? Can we transform it into that? Well, absolutely we can. Sure. So, how do I put something like this into standard form? Well, I'm going to just start messing with it. I'm going to first of all get rid of my parentheses by foiling. So my first terms are x squareds. Then I have a positive 2x. And I have a negative 2x. And I have a negative 4. Plus 19 is equal to 10x. These are gone. So on this side I have x squared plus 15 is equal to 10x. So I'm going to subtract my 10x across, and that's standard. Is it not? It is. We have a equal to 1, b equal to negative 10, and c equal to 15. Okay? So now we have x is equal to 10. I have a negative 10, so I want the positive 10 here. Plus or minus negative 10 squared minus 4 times a times c. Okay, I'm very crooked here. All over twice a. Simplify. 10 plus or minus the square root of negative 10 squared is 100. Minus 4 times 1 is 4. 4 times 15 is 60? Is that right? I think it is. I don't know that I want to start messing up this early. 4 times 15 is 60. Okay? 2 times 1 is 2. All right. 100 minus 60 is 40 over 2. Now before these were all perfect squares and they came out and then we simplified. Well, this time it's not like that, is it? 40 is not a perfect square, but there is a perfect square underneath it, so we do have to reduce it down. If I put this in right now, it's going to say your answer is correct, but it's not in the correct form. Okay? So we have to make sure that we have all of our radical rules down. This is 4 times 10. Now I can split this with my product property. And that 2, which is the square root of 4, can come out. Okay? Now I have to split. Each piece needs to get divided by 2. So I have 10 over 2 plus or minus 2 square roots of 10 over 2. Okay? 10 over 2 is 5. These are gone. Root 10. So now I split into my two different solutions for my math lab. I've got 5 plus the square root of 10 and 5 minus the square root of 10. Okay? So these are my solutions. Now if I threw those into the original, I would get a true statement in there. That's going to be tough to do. So how would I check something like this? Well, I would have to check this equation here, this x squared minus 10x plus 15. Okay? I can't put this in there because it's not. Well, you know what? I can though. Let's just do this. I have to have it set to 0, plus 19 minus 10x. This I can put in there. So let's just subtract the 10x across and not mess with this at all. And let's see what we get. Okay? So first of all, what I want to do, now I'm just trying to give you some ideas for checking your work. First, what I want to do is I want to get some decimal equivalencies on this because I'm going to have to trace those solutions. Okay? So 5 plus root 10 is 8.1623. And 5 minus root 10 is 1.8377. Okay, so that's where these things are going to be crossing. So let's go back up here. Where is that? And put that in. That big, messy, icky thing, but who cares, right? It's a calculator, you can handle it. Put that big, messy thing back in there. Plus 19. As long as you got it set to 0, that's all that matters. Minus 10x. Let's first of all graph it and see if we're even on the right track. All right, so where did we say this was crossing? Almost at 2, that's this one, right? And almost at 8, that's that one. A little over. So this is looking pretty darn good. So in order to get these exactly, we're going to have to use our calculation button in here. So we're going to want to do second function, calculate. What do we want to calculate? We want to calculate out our zeros. So we want a number 2. It's going to want me on the left side, so first of all I have to find it. I don't know where my little, where's my spider? I think it's going the other way. Let's try going this way. Do I see him yet? What? You know, there he is. There he is. All right, so the left side is on top. The right side is underneath. And we want to guess 1.8377. Boy, that's almost right on, isn't it? 1.8377. Now I want to find that one. So again, I want to do second function calculate. I want the 0. And I want to go to the left side, which is underneath on that one. Gotta go just skipping around here. Okay. The right side, which is on top. 8.1623. Nice. So you're going to have to change these into decimal equivalencies to check through the calculation button. So some of these you can't use the calculator to help you find the answer because there's no way we can get that into radical form. But we can certainly check it with it, which is a really nice option. So here we would want 5 plus root 10 and 5 minus root 10. So these are the exact answers that it wants. It wants the exact answers, but when we check it, we can approximate. And since these are approximated the same, then they have to be correct. Okay? So you can really see why we needed all of our radical rules, why that whole radical chapter was ahead of all of this stuff, because we really use it quite a bit. And I think I'm going to, oh, okay, I was going to say, I'm going to leave you alone. No, I don't think so. Okay, we'll for sure do that one. I'll get you started on that one. I just want to see. Okay. Does it matter whether we have fractions? Well, no, not at all. Can you get rid of the fractions? Well, sure. You've got an equation, so you can always get rid of the fractions if you want to. How, you ask? Well, I mean, this would be kind of a mess to put this into the quadratic formula just because it's got fractional stuff and you're squaring and blech. I would hate it. I would almost rather wipe them out. Multiply by your LCD, which is 15, right? I've got a 5 and a 3. If I multiplied every piece by 15, I'm going to wipe out my fractions. It's the same equation. It's just easier to use. So I'm going to multiply each piece by 15. Okay, so I'm writing this 15. Okay, I've got 1, 2, 3, 4 pieces. So 15, 15, 15, and 15. All right, so here we have 15 fifths, which is 3. 3 times 3 is 9. Now, if that doesn't make any sense to you, or if you can't do it like that, I can do those pretty quickly. Use your calculator. We've got 15 times 3 fifths. 9, okay? So however you want to do it. This is a solid 15K because there was nothing there. And then this would be a negative times, why did I put this negative here? That's supposed to be a positive since I've got the negative there. I don't want a double negative in there. But 15 thirds is 5, and 5 times 10 is 50. So this has to stay a negative. If it's, these two have to stay negative, and this one has to stay positive. And that is equal to 15 times 0 is 0. Work with this one instead. Yeah, you've got some bigger numbers, you know, but they're not fractional. So plug that into the quadratic formula and go from there. Okay? Not going to do all these for you. All right, same thing here. Using radicals and I as needed, but then there's no real solution. Interesting. All right, so here we would start to mess with it. I would get rid of the parentheses by distributing first. 4 times 14 is 4 times 14 is 56. Where's my k? Good grief. 56k is equal to 14. Then I would subtract my 14. I have to have this thing set to 0. And again, throw that in the quadratic formula. All right, I will do some complex solutions toward the back. Okay? All right. So, what do we got going on here? Well, we've got something called the discriminant. Am I already at the bottom of my screen? I am. All right. Okay, so what is the discriminant? Well, it's a piece of the quadratic formula that sits underneath the radical sign. Okay, so this is called the discriminant. Is the b squared minus 4ac. Okay, it's not the square root of that, it's just the b squared minus 4ac. I see that all the time, that people put the square root of it. It's not, it's just this piece of it. Okay, do you see that that's actually, when we, hang on, let me write out the quadratic formula here for you. Do you see that it's the piece that sits underneath that radical? Not including the radical? Okay. So we're going to evaluate the discriminant. All right, and it's going to tell us something. All right. If I have a number underneath here that's positive, let's just say when I did this, it turned out to be like a 9. Okay, and I took the square root of 9 for 3. I'm going to have a plus or minus 3. Therefore, I get 2 solutions, right? So if my discriminant, which I'm going to call a d, is bigger than 0, it's just a regular number, whether it's the square root of 40, the square root of 9, the square root of anything that's a positive value, I get 2 real solutions every time. What if this was equal to 0? What happens then? The square root of 0 is 0. What happens to this? It goes away, doesn't it? And all I get is the minus b over 2a. I get 1 solution. So if d is equal to 0, I get 1 real solution. We're going to practice this. And what happens if this is negative? How can I take the negative square root? Remember we had the square root of negative 11? And what did we find out? There weren't any real solutions. Well, there's 2 imaginary solutions to that. So if d is less than 0, then we get 2 complex solutions. Now graphically, what do these things look like? Well, here, let me just, I want to get rid of this so I can draw beside them. Okay. All right, so 2 real solutions. Well, that's going to look like, graphically, this. Okay, it's crossing here and it's crossing there. 1 real solution is going to look like this, where it just touches in one spot. It's got that double root. And 2 complex solutions, we already saw that. That was the one that looked like this. It never touched the x-axis. So we can tell graphically what's going on, and we can also tell by the discriminant what's going on. Okay? So here it's asking us to evaluate the discriminant and to see how many real solutions there are. Well, let's use our calculator. 2. We're going to do it both ways. So we have 7x squared plus 19x, so we can kind of see what to expect. Minus 6. I want to graph that. You see how it crossed twice? That's one of these which we've got 2 real solutions. We don't really, I don't know if it's going to want you to find the solutions at this point, but there are 2 real solutions. Okay? So when we do this, we should have a discriminant that's positive, bigger than 0. Well, let's find out. If I have 7x squared plus 19x minus 6 is equal to 0, I have a is equal to 7, b is equal to 19, and c is equal to negative 6. All I want is the b squared minus 4ac piece of it, not the square root. So I want the 19 squared minus 4 times 7 times negative 6. Okay, I'm going to need my calculator over here for that because I'm not that good. I'm not even close to that good. 19 squared is 361. And I have minus, and this is 28 times negative 6. 28 times negative 6 is a negative 168. Subtracting those two means I'm adding them. So I have 361 plus 168. My discriminant is 529. Okay, I don't really care so much what it is, 529. What I care about is it above 0, below 0, or equal to 0? Well, I've got a positive value here. It's above 0. So that has to be two real solutions. Okay, and I did check that graphically. When I looked at my graph, there are two because it crosses twice. So we have two real solutions there. Okay, now what we want to do is we want to look at the graph. Where are we? We're probably, okay, sorry. This one is touching once. This one is not touching, and this one's touching twice. So it's got to be this one, correct? Kind of looks like what we have. Is that it? That's it? Okay, let's try another one. All right, so again, we're going to, now remember we didn't put the square root over this. We just had just that number. Okay. I know I'm going to say that a million times. I'm going to drive you crazy, but I see it all the time. Let's try another one. We have a equals 1, b equals minus 2, c equals 1. Okay, so all I want is the b squared minus 4ac piece. That's the discriminant. So I'm going to have negative 2 squared minus 4 times a times c. This is 4, negative 2 squared, minus 4 times 1 times 1. What is that? That's 4. 0. Okay, my discriminant is 0. What does that tell me? When it's equal to 0, I get one real solution. It should be touching in one spot. Let's check that out to make sure before. Let's just say this is a test. Before I put that in, I want to make sure that that's what my picture looks like. Okay, 2x plus 1. I want to graph that and see, does it just touch? Yep, it just barely comes down, nicks it, and goes back up. So this is looking really good. So that would mean that my discriminant is 0, and that gives one real solution. And as far as my graph goes, well, again, this is crossing twice, this is not crossing, and this is crossing once. That looks just like my picture here. So I'm going to pick C. Okay? This is turning out to be a really long video. Okay. We still have to do a complex one yet. My goodness. All right. Here, we can't even evaluate the discriminant until we've got it into standard form. So we're going to have to distribute. We have to have standard form equal to 0, so we have to subtract my 2 across. Now that's standard form. So now I can say A is 1, B is negative 3, C is negative 2, right? B squared minus 4AC gives me negative 3 squared Minus 4 times 1 times negative 2. Negative 3 squared is 9. Minus 4 times 1 is 4 times negative 2 is negative 8, right? That's like 9 plus 8, which is 17. Okay, should we check that? Nice work. What does that tell me? It's a positive value. Positive values give two real solutions always. And then we pick out the graph, which we don't really even need, do we? Here it's crossing. What is this line? Isn't that weird? That's the 2. All right, let's put in the original. Let's just subtract the 2 across. So we have x. I know what they're doing there. I didn't want to get into that. Minus 2. Remember, we have to have that set to 0. And so just disregard this line right here. Which one does it look like? It looks like that one. Nice work. Because we have the 2 is up here, not down there. It's not a negative 2. Yeah, I didn't want to get into that, and I'm not gonna. They're setting this equal to 2 instead of 0. So just forget that. Just look at the picture and see which one it matches. Okay. All right, so far what we've seen is we've got solutions. We just put in, like 2 and negative 5. Now it's asking us for the x-intercepts. Okay, x-intercepts are points, correct? So we have to have ordered pairs for our x-intercepts. All right, that's the only difference. What's your y-coordinate on your x-intercepts? Well, those are 0. Okay. So let me just, I'm not going to do this one. I'm just going to check it 3 times, just to see. Okay, it doesn't want the zeros. It doesn't want the ordered pairs on there. It just wants the solution still. All right. So what we get from here is that the x-intercepts are the solutions. There's no difference between if it's worded the x-intercepts or if it's worded the solutions. It doesn't matter. Okay? Which is really unfortunate because an x-intercept is an ordered pair. Some authors like the ordered pair version and some like just the x equals. So it depends on the author. I'm not going to do, I think I'm just going to do one of these for you, and then I'll be done. This is an awful long video here. I try to keep these under an hour. The hardest part about these, by far, is the simplification process. Yeah, I mean, it's super easy to get these in standard form, and it's super easy just to plug it into a formula. I mean, how hard is that? It's always the simplification piece of it that's really a bugger. Okay? 1, 5, 7. So I have x is equal to minus b, which is minus 5, plus or minus the square root of 5 squared, minus 4 times a times c, all over twice a. See, that's the easy part. Now what to do with that? Minus 5 plus or minus, what do we have? We have 5 squared, which is 25, minus 4 times 1 is 4 times 7 is 28. 2 times 1 is 2. 25 minus 28 is negative 3. Now, obviously, we don't have any real answers because we've got a negative underneath there, correct? But there is no other choice as far as there are no real solutions. We have to get the complex solutions in there. Okay, let's just verify that real quick right now to make sure that this thing is indeed hanging in the air, that it's not crossing, so that we know that we have complex solutions. And how do you find complex solutions on the calculator? You don't. You can't find them. See how it doesn't touch? And there's no way that you can find them. Okay, so the only way that you can check these is by throwing them back into the equation, and that's going to be really difficult to do because you're working with negatives, square roots, which are imaginary, but you can do it. Okay? All right, so now what we want to do is we want to simplify this. How do we do that? We have -1 times 3, right? Remember, the square root of -1 is perfect. That's a perfect square. It's got to come out. Square root of -1, we can split these with our radical rules. Okay. Now, if this was bigger, let's say it was like a 20, then I'd also want to take the 4 out. But since it's just a 3, that we can't do anything with that, we just take that -1 out. So we have -5 plus or minus I roots of 3 over 2. Now, what are my radical rules? I can't have a radical in the denominator. I don't. I can't have a perfect square underneath my radical. I don't. I have to make sure that my outside pieces are all simplified. Well, I can't simplify anything in here, so I'm finished. Okay? So we're going to have to transform it into the a plus bi form. Okay, so far as my radical rules are concerned, I'm finished. But if I want to get into my a plus bi form, then I have to keep messing with it. So I'm going to want to split this. So each piece gets divided by 2. And now I'm done because this is my a plus bi form. My a is -5/2, and my b is a 1/2. Do you see it right here? There's really a 1 there. 1/2 I. No, my b, excuse me, is 3 square root of 3 over 2. And then I have my I. Okay, so let's see how we're going to get that in there. How do we get that in there? Oh, let's see here. Let's do a fraction with a -5, whoops, over 2. And we want to do plus, and I have another fraction, and I've got an I up there, and then I've got a square root of 3. This is going to be really messy, over 2, comma. And then I have a fraction. So I got to get both of the positive and negative values in there. Then I got a -5 over 2 minus, then I have another fraction, and I've got I roots of 3 over 2. Nice. Okay, so check in your work. I suggest that you go back through this and check this. Check every little step to make sure that you've got it correct. The calculator is not going to help you, and to get this back into here to check it will be a nightmare. Okay? So what I suggest on these complex ones is go back through here and just, make really good notes as far as your steps go, and just check every single step for accuracy. That's going to be much quicker and much easier than trying to get these back in there. Okay? Because I can't check this with the calculator. There's nothing to check. There are no zeros. The zeros are where it crosses the x-axis, and there aren't any. Okay, so these are all the same. It's the simplification that's really the hard part. All right, so what about something like this? Well, I'd want to get it into standard form first. X squared equals x5 minus x minus 7. I want to get rid of my parentheses, so I want to distribute that x through minus x squared minus 7, right? And then I want to bring everything this way. So I want to subtract this, I want to add that, and I want to add that. Can I also bring that this way? Yeah, that's easier. Just bring that way. It doesn't really matter what we got going on here. Okay, I just have to set it to 0. So 0 is equal to 5x. I've got minus 2x squareds minus 7, and I'm going to put that in descending order so that I know what my a and my b and my c are. A is -2, b is 5, c is -7. Proceed from there. All right? So this might be a little bit trickier on the simplification, but it's really going to take into consideration all your radical simplification rules, whether they're real or whether they're complex. All right, so take your time with this section. It's not an easy one. Be real precise about things, make really good detailed notes so you can go back through it, you can check it, and the quadratic formula is just such a great thing because it'll give us, you know, any kind of solutions. It doesn't matter what kind of solutions they are, and it solves all quadratics, every and all of them. Where factoring is very particular and it only solves just a few. So you have to be, you know, you have to have something that works for everything, and that's our quadratic. And don't forget about what the discriminant tells us. It tells us either graphically or how many solutions that we've got. Okay? All right, well, good luck with this section, and I will see you for 11.5.